Alright, good morning and Merry Christmas. So, I thought what we were doing last night was pretty interesting, so I thought we would continue. So, it was this idea about putting the circumcircle of a triangle and making it the unit circle on the complex plane, okay? So, the center is the origin. Um, so, there was this fact about, um, so O is obviously the origin. The centroid was given by a third a plus b plus c, and the orthocenter was given by a plus b plus c. Okay, so with all these things, I think it'd be good if you try to prove some of these things yourself um, before seeing how it's done. But I thought it'd be cool to kind of go through it anyway. So if you want to pause, you can. Okay, so yeah, so I guess um, for the centroid, it's like the midpoint here is half b plus c. Right. So then the line joining um, a to the midpoint is just half b plus c minus a. Okay. So that's this line here. And you know that the centroid, the intersection of these medians, is 2/3 of the way along, right? So if you times it by 2/3, that'll get you this arrow joining G, right? And so that'll be just G minus A. So then if you add A to that, you should get the coordinates of G, okay? Because I guess this way of doing it both shows that it works and it's actually correct. Okay, so if you simplify that, you get G. Okay, now for H, so H, I guess if you know the Euler line thing, it should. So also for the G, it doesn't seem to depend on the unit circle at all. Okay, this seems to be the formula no matter where um, A, B, and C are positioned. Okay, so this is not a unit circle result. It doesn't seem. And for H, we know about the Euler line, so we know H now has to be a multiple of A plus B plus C. Okay, and so I guess the thing in so you know so one way to check it is you could check it without knowing where it came from. So if you had H, then AH is just B plus C, right? It's H minus A. And basically, if you could show AH is perpendicular to BC, and all the other combinations of these kind of things, then H must be the orthocenter. So basically, you want to show that B plus C on BC or CB. You can say B minus C or C minus B. There is elements of the imaginary numbers. That was like the lemma. Okay, so that's how I guess they would have done it in the notes. And to see something's imaginary, like Z would be imaginary if Z is Z plus Z bar, Z minus Z. I guess z bar equals minus z. That could make it imaginary. Okay, this would be like x minus iy equals minus x plus iy. Yeah, and so for this to be true, the real and imaginary parts have to equate, so x has to equal 0. X to be equal to minus x. Alright, so we're assuming that x and y were real. So, in the notes, I think they would have taken this expression, okay? And so this is where I encourage you to try it yourself, because that's probably not the most natural thing you would do, given this. But if you were given the lemma in the notes, that might be. And so you could take the conjugate of this and show that it's equal to the negative of the expression. Okay. But I thought another thing that might be more illustrative of what's going on, okay, is if you're trying to compare b plus c and c minus b, okay, and see they're perpendicular, one way is to see where they lie as vectors. So b is like this vector here, right? And c is like this vector, right? So let me erase this other stuff. You can draw this parallelogram. This is also b, and this is also c, okay? And then we know that c minus b, so this side bc, cb, this is c minus b, right? That's one of the diagonals of this parallelogram, okay? And then we know that b plus c is the other diagonal of the parallelogram, okay? And the fact that these are unit vectors on the unit circle makes this a rhombus, okay? So therefore the diagonals meet each other at 90 degrees. And so I guess that makes it clear exactly where you use this assumption that they're unit vectors. And it's not exactly used in a huge way, but it kind of, so I guess if you don't use it, you might have a scalar here that's not nice. But if you do use it, you end up letting the scalar equal 1. Okay. So, yeah, so that's a pretty cool theorem. And actually, there's some other things that are interesting too that'll help you with that example that I didn't mention. So another thing, so it all comes from the simplifications you get when you assume that things are unit vectors, okay? So remember we had this formula for the reflection of z about AB, right? AB, and we reflected z to W, right? And we had this formula, it was W equals, it was like A bar minus B bar, A minus B, Z bar, what was it? It was minus, then plus A bar B, minus A B bar, yeah? Okay, so maybe you want to try this for yourself first, but if A be a unit vector, this formula simplifies dramatically, okay? So what does it mean to be a unit vector? So A equals 1, right? So this is also A times A bar is equal to 1. So they're sort of reciprocals of each other, okay? So, yeah, so you might want to try this yourself, but, okay. So So look at how things simplify. For example, I could multiply the top and bottom by AB, right? So I get AB times A minus B Z bar. And then when I times this by AB, the A cancels with A bar, and you just get B squared minus A squared, right? And on the bottom, you get B minus A. So if you times top and bottom by AB, you get that. And now there's a common factor of basically B minus A, yeah? So you can cancel. So this will become minus AB Z bar, and this will become B plus A, right? And you cancel the bottom. So the formula becomes A plus B minus AB Z bar when A and B are unit vectors, okay? So that's pretty cool. I think hopefully you can continue to try and do that example yourself. And I am pretty interested in going through the example. But obviously it's more satisfying if you do go through the example yourself. And I would imagine how the example would go now. Okay, so try that.